Hello, welcome to Gme-A Live and to today's lecture on man-made stones. I'm Julia Griffith from jewelryadvisor.com and let's look at what we'll be learning today. So focusing on our learning outcomes, we're going to start by just defining some terms to do with natural, artificial and synthetic gemstones. And then, because this is such a large subject, it was very ambitious to choose this as a topic today. We are going to focus on just one part of man-made gemstones, which will be synthetic gemstones, which are arguably the hardest to identify out of all the artificial materials. And more specifically, we'll be focusing on the most common gemstones of also the most desirable gems. So we're going to be looking mainly at synthetic emeralds, synthetic sapphires, rubies, and also synthetic diamonds. So we'll be looking at manufacturing methods as well as identification features, which is what we're all here for, isn't it? So let's start off with some definitions. So starting with natural materials, natural gem materials are those that have been formed completely by nature without any interference by humans. The only exception to that is cutting and polishing, so the fashioning of gems. When we're referring to artificial materials, really we're talking about, well, the opposite of that. So we're talking about gemstones that have been made by man, so that have been made in laboratories or factories. And this can be completely or just part of the gemstone. All of these are classed as artificial products. So really, there are three different groups that artificial materials can fall into. The first group that we're going to talk about briefly are artificial products that are made from gemstone components. So when we're talking about this, we're talking about composite gemstones and other manufactured products as well. So composite gemstones are those that are made out of two or more parts, as in this example here. These are all pseudostones that are made out of a colourless crown and a colourless pavilion and then coloured glue. And these are made to imitate other gemstones. Other manufactured products that we could be referring to could be reconstituted or reconstructed materials such as pressed amber. So when you have lots of amber chips that are then pushed together, even though it's made out of natural components, the material resulting from it is an artificial material. Also ambroid, which is when you sinter powdered amber and push it together to make one solid mass. And also things like lead glass filled rubies would come under here as well. And can I think of anything else? Not right now. But that's one type of artificial material, the one that's made out of components of gems. The next group of artificial materials are those that are completely thought up by man, well, I say by man, by humans, completely thought up by humans and that do not exist otherwise in nature. So examples of these materials include plastic, paste, cubic zirconia, commonly known as CZ, and then also I've got YAG and GGG at the end here. YAG stands for yttrium aluminium garnet and GGG for gadolinium gallium garnet. Now, all of these do not exist otherwise in nature. So for plastics, complete man-made creation, and these are excellent for simulating or imitating organic gemstones. So this box here imitates tortoise shell. Here we have plastic imitating amber. It's also great for ivory imitations or coral imitations. Also shell cameo imitations. Plastic is common within a lot of costume jewelry, especially for imitating these organic gems. Paste is also a very common material used in costume jewelry. Paste is man-made glass, and this can be made in any color and to any transparency as well. So it can imitate almost all gemstones, really, but it is otherwise a completely man-made product. Cubic zirconia, again, something that's not found in nature, although it is in an inclusion in one particular gem, but that's it. And we found that out later on after inventing this gem here. But cubic zirconia can be created in every color. So again, imitating all sorts of crystalline gemstones. Most commonly though, our colorless CZs will imitate diamonds. And then YAGs and GGs, even though these are technically garnets, these types of garnets do not occur in nature. And likewise, garnet itself can't be created in a laboratory that you find in nature. So you can't get synthetic almandine garnet or tsavorite garnet. It's not possible because garnet is very complex, as you'll know if you study gemology. So that's our second group, so materials that do not exist in nature. And everything that I've mentioned so far, the main use is for imitating other gems most of the time. So these really are very easy to identify for a gemologist because they have their own unique set of observations that we can identify the material from. And if not, or as well as, we can also then do gemological tests where we will have a unique set of gemology results or gemological test results that will then point to an identification. So identifying most artificial materials is not too much of a challenge for the gemologist. It's really the main point of our job is to know what gems are what. But the third type of artificial materials, well, these are the materials that also exist in nature. So these are the synthetic materials or the laboratory grown materials. Now, these synthetic materials, well, identifying a synthetic, this is where gemology can get a bit tricky because synthetic materials are the same chemically and physically and visually as, as those that have formed in nature. So just to have a look at the definition of synthetics a bit closer. So these are also known as laboratory grown or lab created gems, depending on, well, what organizations you follow or what organizations you're a member of. Some organizations prefer to use the term synthetic, some prefer to use laboratory grown or lab created. As long as it's clear when we're defining the stones, everything's fine. But a synthetic material is an artificial material, so one that has been made completely by humans, completely manufactured, but it does have a natural mineral counterpart. So in nature, there is something that is the exact same chemical composition and crystal structure, and therefore, because of those two things, it also has the same physical properties, so the same hardness, the same toughness, the same type of cleavage if it has cleavage, and also the same optical properties. So the same luster, the same ability to produce fire, so the same dispersion. Everything is the same. So that's why it can be very difficult to identify these materials because we can find out the identity of the stone. We can say, oh, that's a beryl and it's green, so that's an emerald. But then finding out whether it's of synthetic or natural origin is where it can be a bit trickier. But clear disclosure of these materials is of utmost importance because there is such a big difference in value. And the reason that there's such a big difference in value is because there is a difference in rarity of these materials. Those that have been created are less rare and can be made, well, as many as you like in very large sizes and of good qualities compared to those that form in nature. So therefore, there is this price disparity. And for that reason, identifying it is of key importance for gemologists. So let's talk about what gem materials can be synthesized, because it is a finite list. Not all gems can be synthesized. So we have beryl. So our beryl group, our beryl species, this can be synthesized in all colors. So you can have emerald, which is your green, morganite, which is pink, aquamarine, which is blue, goshenite, colorless, heliodor, yellow, red beryl. All of this can be synthesized, but most of the time it's just emerald. So the main, most popular gem is the one that's synthesized. Corundum can be synthesized, so that's ruby and sapphire. Diamond, although we can grow colorless yellow and blue synthetic diamond, we can also create all the other colors from further treatments as well. But colorless diamond is currently the most popular color for synthetic diamond. And we can also make chrysoberyl, which is normally a synthetic alexandrite, the color change variety. And also quartz is largely synthesized as well. And again, we can use or we can create a number of colours, so colourless, rock crystal, purple amethyst, yellow citrine, or a mix of these last two, which is ametrine. So these are the main gems that you do see, and it's our job really to tell the difference between those that have been created naturally or those that have been synthesized in a lab. We're going to focus on just 4 of these today, so these top 4 gems here: emerald, ruby, sapphire, and diamond. There are a few more synthetic materials that I will just mention. Oh no, I forgot spinel. Oh dear. Also spinel. So spinel is one that we can create synthetically as well in every colour that natural spinel can come in, as well as a few more. But the only exception to that is purple. We can't make purple synthetic spinel. A couple more gems to mention would be synthetic rutile and synthetic moissanite. So these are 2 gemstones that if you do find as faceted versions, you can know that these are of synthetic origin. They've been made in a laboratory. The reason is that although these materials both occur in nature, rutile, you'll be more familiar of it as an inclusion inside quartz or inside corundum, but it doesn't grow to sizes that can be faceted. And also, it's not normally transparent like the synthetic rutile is either. So if you see a gemstone that you test and discover it's synthetic rutile, it's going to be a synthetic rutile. And likewise with synthetic moissanite, although moissanite occurs in nature, it's often of low quality, so non-gem quality, and also of really small sizes. So if you have a test for a moissanite, it's going to be a man-made synthetic moissanite. Some more materials to mention are synthetic opals, corals, lapis lazuli, and turquoise. Depending on which association you talk to, some people class these as synthetics, some people don't class these as synthetics because there is some additional reagents in their structure, which technically don't make them true synthetics, and also a slight difference in structure. So these are sometimes thought as synthetics, sometimes not. But I thought I better put them in there so I'm not ignoring them completely. And also there are reports of synthetic peridot being made and fosterite as well, but these are not commercially available, so not widely available. So let's look at why we create synthetics in the first place. What was our motivation? Originally, this was all for industrial uses. So this is the case with many developments within any inventions and any creations that we have. It's for some kind of use in industry. Gemstones, because they have such desirable properties beyond their aesthetics, they are incredibly desired for use in industry. So, for example, corundum, heavily used as abrasives because it's got very good hardness. Also, for very high purity ruby crystals, these are excellent for lasers. Quartz is widely used in industry. You probably have it all over your household without even realizing it, because quartz has some fascinating abilities to keep vibrations at a really consistent level, and also a phenomenon known as piezoelectricity. This means that it's used in an awful lot of different inventions. I can't think of the word I'm really looking for, but lots of pieces of technology. So, for example, it's within the airbag system within your car. It's actually what sends the signal to launch the airbag. It's also within navigation systems, and also in our timepieces as well. So widely used is quartz. And then we have diamond. Diamond is again very desired within industrial settings because of its hardness. So we have diamond drill bits, diamond saws, so to cut and drill everything effectively. So diamond is so desired that actually the majority of diamonds that are used in industry are all synthesized because the natural production is nowhere near the demand. So I think the natural production for diamonds, well, it's over 100 million carats of industrial quality each year. That doesn't even make up 1% of what is needed in industry. So most of it has to be synthesized. So very, very interesting. And as well as these kind of industrial uses outside of our industry, we use it in our own industry as well for cutting and polishing gems. So here's, for example, a diamond lap with diamond powder. And also now we create synthetics, and we have done for the last 120 years, so that we have more products in the jewelry market. So we have these products that are a lower price point that visually look a very high quality. So that's also why we create synthetics. To briefly look over the history of synthetics, the first commercially available synthetic came about in 1902, and this was the Verneuil Flame Fusion Ruby. There are reports that Pierre Verneuil, who created this synthetic, did come up with the process in the 1880s, but he didn't commercially launch it until the 1900s. Uh, Over the next 100 years, you'll notice that lots of different synthetics came onto the market. The reason is that a lot of research happened really from the 1700s into the 1800s to do with chemistry, because this was really the boom time for chemists and chemistry and that science, because all the elements were discovered. And so lots of experiments were happening to create all sorts of things, to find out what things were made of and to find what we could create as well. So, really, in the last 120 years, all sorts of things have been created. So, the next synthetic to be made, there was crystal pulling ruby that also happened in the early 1900s, and then spinels came about in the early 1900s as well. This again was by flame fusion. Actually, it was an accident. The creator was trying to make a synthetic blue sapphire. But blue sapphire, even now, is really hard to create synthetically. So accidentally, he made synthetic blue spinel. And the reason that that came about is because corundum is aluminium oxide, spinel is magnesium aluminium oxide. So during experiments, created a completely different material, which is quite fun. Uh, Flux grown emeralds came onto the market in 1935. So that's when emeralds started to be synthesized. Then quartz, hydrothermal quartz, that came into the market just after the Second World War in the 1940s. The reason for this is because there was a huge demand for this material post World War II. Otherwise, they'd been tinkering with this method since the 1890s. For the same reason, for the importance of the material diamond, there was also a race to synthesize diamond after the Second World War as well. And lots of people became successful actually at doing so. And HPHT and CVD diamonds were successfully first synthesized in the 1950s, again for use in industry. There was a few more different synthetics that then came in around these times as well. So the 1960s, flux-grown rubies came onto the market, and also in the 1960s, hydrothermal emeralds came into the market. So even though the method may have been created, they have to tinker and experiment to create the different types of gems. So here is a summary of the different methods of synthesis. So these are the ones that are mainly used within the gem industry today. So we have our Verneuil flame fusion, which creates a number of different types of gems, flux growth, hydrothermal. Then we have HPHT and CVD. So these create diamonds and diamonds only. And then we also have crystal pulling and zone melting for corundum and chrysoberyl as well. Now, we're not going to focus on these bottom two during this lecture, even though they create corundum. The reason for that is these particular techniques grow larger crystals of really high purity. So these are quite expensive and are also more often used for lasers for industrial uses instead of gems. And due to their high purity, even if they were made into gems, there's nothing visual there for you to detect them with anyway. So for this session, we're going to focus on the most common, so the big four gems, if you like, ruby, sapphire, emerald, and diamond. And we're going to focus on the most common methods that these are synthesized by. And we're going to talk about how these methods grow the various gems. And then we're also going to focus on the identification features of each type of synthetic. So let's look into how to identify a synthetic gem. This is a bit of an overview to start off with, so one that can apply to all synthetics. The first thing you need to do is identify the species and variety of the gem. So this is by normal gemological testing. So find out what your gemstone is. Where some gemstones can't be synthesized, such as tourmaline can't be synthesized, or any of the garnets can't be synthesized, due to that, that's kind of a shortcut to knowing whether you need to look for synthesis or not. Because if they can't be synthesized, well, then you know it's a natural gem. You just have to determine whether it's been treated or not. So, but if it is one of the ones that can be treated, so corundum, chrysoberyl, spinel, emerald, diamond, then that's when we have a bit more work to do. We need to find some features that positively confirm the identity as either natural or synthetic. Some general observations that you'll notice when you see a synthetic will be that the stone often has good, consistent colour, often a very desirable colour, kind of the best of the best. You'll also notice that the stone in general is loop clean, so it can have very good clarity, and you'll probably notice that there's a lack of natural features in there as well. You'll notice that these are typically very well cut. So by well cut, I mean to very symmetrical shapes, to very neat angles, and also often to calibrated sizes. When we talk about calibrated sizes, I mean sizes that are suitable for mass-produced jewellery. So for example, 5 by 7 millimeters or 6 by 8 millimeters, ones that can be made in mass and then put in to mass-produce mounts very quickly. Also, these can be of a larger size than you'd expect to see in nature, or at least, rarely see in nature. Now, all of these things, this is what synthetics often embody, all of these things together. But we can't ignore the fact that this combination of features can occur in very high quality, rare natural stones as well. Because when we're making synthetics, often we're trying to look like the best of what nature can make. So it's when you have really a gem that can be too good to be true, that's when you have to ask yourself the question, okay, well, either I've got a very nice, rare, natural stone, or I have a very, mass-produced, common synthetic. So this is really the fork in the road, how you have to make your decision. And the only way we can make a decision really is for concrete evidence, for real proof that prove that either it's natural or it's synthetic. And we're going to find that within inclusions and features. But this is still quite a good thing to look for, because also this kind of makes up a whole set of features along with other features that we might see later. Also, there can be other types of circumstantial evidence that can help our identity, although we should always take these, with a pinch of salt. But some other circumstantial evidence could be what the stone is set in. So, for example, if it is set in silver or even a base metal, chances are it might not be a very fine Burmese ruby. You never say never, but so that's circumstantial evidence. Also, you can look at the number of stones. So, for example, to get a suite of perfectly matching or the same size or the same color, perfectly matching stones is really difficult. Although it can be curated over time, these suites are very, very rare and they're very expensive. So if you do happen to see many gems together that have this good color, good clarity, are all well cut to the same shape and sizes, well, that leans towards the fact that these might be synthetic stones. An example of this, I was in Tucson and I said to a vendor, oh, what are these stones? And he said spinels. So I looked at them and said synthetic, and he said yes. And the reason it was such a short exchange is because there was 50 spinels that looked fabulous. So if they were natural, then that would be quite an achievement. So let's talk a bit more about how to identify synthetics. So we've got our general observations. Now we require definitive proof, and this will come in the form of specific inclusions that will be due to the manufacturing process. So this might differ depending on the type of gemstone and also the type of method of synthesis used. So that will affect what inclusions we see. Also, some of these gems may have very specific, unique responses to some gemological tests. And lastly, if we cannot identify them from observations or basic gemological testing, we can rely on advanced testing equipment. So either a friend that might have some that you might know, or send them to a lab, depending on how important the identity is to you. So let's talk about these different types of synthetics, starting with Verneuil flame fusion. So this creates these different types of stones, so corundum, ruby sapphire, spinel, and synthetic rutile. The way that it works is your feed powder will drop through this feed tube here into the apparatus. The feed powder, well, it depends what you're making. If you're making corundum, that will be aluminium oxide, so aluminium powder with oxygen gas, and then any colouring element that you need in there as well, chromium if we're making ruby. That will then fall onto a high temperature oxygen flame. Temperature depends on what you're making, but if it's a corundum, that will be 2045 degrees centigrade Celsius. And that will cause the feed powder to melt, and that will fall onto this rotating ball, which has a little seed crystal to start the crystallization process. And as it melts, it drops onto the ball, and then it will start to crystallize as it cools down. And growth is really fast. This grows about 10 millimeters or 1 centimeter every hour. So in just a day, you can have a decent sized crystal. And these crystals are known as balls. So here's a picture of these synthetic Verneuil flame fusion crystal balls here. Here's a sapphire, blue sapphire, and here we have a ruby. When it comes to identifying these stones, so our Verneuil flame fusion rubies and sapphires, the main feature we're looking for are curved striations. So curved striations, this is a directional feature within the gemstone. You will not see it from all angles. And it is best seen with transmitted light. So you need the lights to light up those facets that you're focusing on. I find it best to have my light up high, kind of like my desk lights right here, and I'll have the gemstone here, and I'm looking at the pavilion, parallel to the side pavilion facet. And that's where I will try and get the best angle to have a look for this gem. But you need to look at it from every single direction. Sometimes it's easier through the crown. But when you look for your curved striations, they often look like these transparent parallel lines, parallel to one another, and they curve almost like a ripple effect throughout the gem. And they can either be transparent like they are here, or they can have a slight color concentration to them, in which case they're sometimes called curved color banding, just here shown in this sapphire. So you can see that these parallel curved bands are running up the stone, best seen in the transmitted light. So here, where the light's not being transmitted, you can't see the feature. Here you can. Now, this feature sometimes can be confused with features on the surface, such as polish lines or even fingerprints, but make sure that your hands or your gems are clean, and that won't be a problem. But the way to tell the difference between an internal feature and an external feature is to look at where the feature goes in the stone. So for example, with these curved bands, you will notice that they're surpassing facet junctions. They don't care about the cut of the gem, they're going through it. And that proves that it's an internal feature that's inside the body of the stone. If it was a surface feature, it would be limited to the facet and the facet shapes. So for example, polish lines, you would have them one direction on one facet, and these would abruptly stop or change direction on the facet next to it. So that's how you can tell the difference between internal and external features. With curved striations, unfortunately, we can't see these in all colours of Verneuil flame fusion synthetic corundums. So you don't see it in the paler colours such as colourless, yellow, or the orangey pink Padparadscha lookalikes. So we have to look for other features in those stones, or if it is a very important sale or an important valuation, you may have to send this to get testing, particularly for the Padparadscha lookalike orangey pink ones. Other features you could look for, though, include gas bubbles. The gas bubbles in Verneuil flame fusion synthetic corundums are really small because they are limited to the space where they crystallized. So where that melt dropped onto that crystal ball and you've got the curved striations, the gas bubbles are within there. So they're always going to be really, really small in size. Also, you might see something known as chatter marks. These can also be called fire marks. And chatter marks, fire marks, these are a feature of poor cutting or cutting without due diligence or enough care. And what these are friction marks, friction burns on the facet of the gem, sorry, where it was allowed to get too hot on the polishing wheel. And for that reason, you end up getting, yes, these friction marks on the facet faces. Now, chatter marks and fire marks can happen on any material. It doesn't have to be synthetic, it can happen on naturals. But what it does suggest is that this gemstone maybe isn't very expensive. So if you did have, let's say, a very large good color, good clarity ruby, and it had these chatter marks on, you would think that maybe the cutter would have actually taken more care polishing it. So this just suggests that it's a cheap material. So this is indicative, but be warned, it can occur on everything. Other features to look for are then that checklist I mentioned earlier. They're generally good colors, very bright, they're good clarity, good sizes, and very neatly cut. So all these things together, we certainly have a very clear identity. One more thing, when it does come to curved striations, just to say this is a diagnostic feature for Verneuil flame fusion corundum. In any of the other flame fusion synthetics, you do not get this feature. So if you see this one feature, not only do you know it's a synthetic ruby or sapphire, you'd also be able to conclude its synthesis method, which is the Verneuil flame fusion. Other types of gems that can be made with Verneuil flame fusion are star rubies and sapphires, so those with asterism. And these often have a set of features very different to the natural counterparts. One feature is that they have very straight, defined stars, just as this picture here. The rays of the star often seem to extend edge to edge and don't even need pinpoint lighting to see clear. So the very sharp stars often seen right on the surface of the gem. Curved colour banding can still be seen in these stones, best seen on the back of the cabochon. You will see these curved colour bands confirming its Verneuil flame fusion origin. You'll also notice that these synthetics are flat backed. The reason for this is so they're easy to set within jewellery. They're made to calibrated sizes of very neat outlines, and also typically they have really good colours. Now, this is different to the majority of natural star rubies and sapphires because very fine quality star rubies and sapphires from nature are really rare. And so the majority of them, rather than very well defined stars, the stars can look more diffused and also a bit more into the surface of the gem. They might be off center as well. You will not see curved colour banding in these stones. Instead, you'll likely see hexagonal colour zoning due to their natural origin. Rather than flat backs, these are often left unpolished on the back. The reason for that is these are sold by carat weight. So by polishing the back flat, you are, in a sense, polishing dollars off the back of the stone. So you might find some of them have a curved cabochon at the back, but again, they try and retain weight. To calibrated sizes, these are often cut to whatever the best yield is for the rough gem. And in regards to colour, natural star rubies and sapphires cannot be heat treated to high temperatures. The reason for that is what's causing the asterism is the rutile needles. And if you heat these up to too high temperatures, then these needles will dissolve and dissipate, so ruining or removing the star completely. So often the colors of these materials are often not the most desirable. So purplish red when it comes to your rubies, either colorless or white, pale pink, pale blue, or a golden brown in your star sapphires. There are very, very fine bright blue and bright red star corundums out there, but they are just very, very rare. Now let's move on to the next synthesis method. So onto your flux melt or flux grown synthetics. So we use this method to grow corundum and beryl, as well as spinel and chrysoberyl. And like the name suggests, these are grown within a flux. So a flux is a solid material that when molten has the capabilities of dissolving other materials. So into the flux we put in feed material, which will vary depending on what gems we're growing. We will put lots of feed material and let it dissolve into the flux until it forms a solution. And then once we have a solution, we drop the temperature of the flux, which allows the solution to become supersaturated. And when something's supersaturated, that's when crystallization can occur. And crystallization will occur on the suspended seed plates that we put inside the crucible, and the crystals will grow from here. Now, flux-grown synthetics, these aren't as common on the market, mainly because they take longer to grow and therefore are much more expensive to buy as synthetics, because they're more expensive to create, so they're more expensive products. Growth time can take several months to even a year to grow a good size crystal to be able to cut good size stones from. When it comes to identification features, one key feature is flux feathers. So these occur when there is a break within the growing crystal and the solution can flow inside and will heal the fracture inside out. This often traps flux residues within the fractures, so you end up with these flux feathers. And in the healed feathers, you can see these flaxy areas here. These will be a whitish to orange color and will have a translucent appearance to them. Natural feathers will be transparent and therefore colorless. So that's your flux feathers here. You can also get veils within flux synthetics. So these are veil-like flux feathers, very different to what can occur in natural emeralds, because natural emeralds are often full of open fractures, which have been filled with oil. So these twisted veils in amongst a gemstone that otherwise has no natural inclusions is a feature of your flux synthetic emeralds. Other things you might see are metal platelets. The metal gets in here because the crucible is lined with metal. So the metal will be something that doesn't react to the solution, such as platinum or maybe graphite. So you can end up getting these metal platelets trapped within the finished gems. These will usually be triangular or hexagonal in shape. And when we look at them, shine your light onto the inclusion and it will reflect the light back to you. So it has this metallic reflective luster. And if you had the light transmitting through the gem behind the inclusion, you would see that the inclusion is opaque. Another feature would be your flux cavities. So these are larger areas within the stone that are filled with flux. This photograph shows orangey flux within these cavities here. And finally, comet-like structures can also be seen in these synthetics, which you can see running along here. Now, when it comes to identification, for these stones, you should never rely on just one feature, really. It's good to see a combination of these features together. Flux feathers, though, are pretty diagnostic. And then also you'll look for the other features such as good color, good clarity, otherwise, apart from these features, and a lack of natural features. Additional identification features for emerald only occurs during testing because flux emeralds typically have a lower Ri and Sg compared to natural emeralds. Now, there is a slight overlap here between the RI range of natural emeralds and synthetic flux emeralds, but only a very slight overlap, so just from 7.0 to 1. 1.570 to 1.575, just a little overlap here. And the same for SG as well. So the specific gravity, natural tends to be a little bit higher than your flux synthetics. And again, there's just a slight overlap of 0.03. So that can be a handy extra tests to do as well. Now on to our last synthetic method to do with our coloured gems, and this is hydrothermal growth. So we can grow corundum, beryl and quartz via this method, and this closely mimics any hydrothermal growth that can occur in nature. We use water to create the material ready to dissolve the materials inside this process. So what we do is we have a piece of equipment here known as an autoclave. We fill it up with about halfway with water and also put the feed material inside the autoclave and then seal it shut. Now we then heat it until the water becomes this very heavy, dense vapor, and this is capable of dissolving the feed material within. Now, this is so heavily pressurized that this autoclave it's created in is often called an autoclave bomb, because there have been unfortunate occurrences where these just explode because the pressure is so high. But if all goes well, upon cooling down the autoclave, the solution that has been created inside will start to crystallize on the seed materials or the seed plates that are inside the autoclave here. And quite large crystals can be grown this way. So quartz crystals, for example, can be grown quite large, especially in multiple stages. In regards to growth time, this is in between the two methods we've spoken about before, so moderate speed for growth time, about 5 millimeters every 2 weeks. So you could have a few months of growth to get a decent sized cut gem. To identify the hydrothermal grown synthetics, the main feature that we can look for is the hydrothermal growth pattern. This is also known as heat haze or chevrons as well. Now, this occurs in all hydrothermal grown products except for quartz. So we can see it in emeralds and also in sapphires and rubies as well. And this hydrothermal growth pattern, it looks, well, anything like water can look. So it has this appearance to it, this watery heat haze or chevron appearance to it. And sometimes this can appear quite calm, like in this picture here, or it can be a bit more ferocious, like in this picture just here. You can see these chevron-like appearances here, which is why it's sometimes called chevrons. Now, like the curved color zoning that we discussed earlier with Verneuil, this is throughout the whole structure of the emerald, but you can only see it from very particular angles. So to spot this feature, we need to look at all sorts of directions within the stone to check that this feature is or isn't present. Again, best seen with transmitted light. So as you can see here, where the gemstone lit up, you can see very clearly this hydrothermal growth pattern. Just to show you this feature within other gems, so here it is in ruby, blue sapphire, and also green sapphire as well. So this heat haze effect or hydrothermal growth pattern. Now, this isn't to be confused with a natural appearance that can occur very rarely, but within some natural emeralds. It's mainly associated with Colombian emeralds, and it's known as, oh, I hope I say this right, it's known as the gotu de aceite phenomena, also known as the oil drop effect or drop of oil effect. And this also is kind of a watery appearance within the stone, often compared with the silkiness of cashmere sapphires. It allows the colour to disperse throughout the stone very well. And it's quite a desirable effect that you can get in Colombian emeralds, but very, very rarely. It's considered to only be associated with the finest stones, and they say only about 1 in 1,000 fine Colombian emeralds show this feature. But if we look at it up close, it could be confused, I suppose, with the hydrothermal growth pattern. But up close, you can see it from more angles within the stone. And also, if you look down the C-axis of the gem, which you would be able to find under the polariscope, you can see it's kind of hexagonal in appearance, parallel to the C-axis, and perpendicular to the C-axis, you get these longer appearances to them, so more columnar appearances. So it's a phenomenon not widely seen, but something to be aware about. Another feature that you can see in hydrothermal growth synthetics, and this is for emeralds only, is you might see nail head inclusions. So nail head inclusions, these are, well, they look a bit like nails. They are a nail-shaped cavity, and at the very top they have a phenakite crystal. Phenakite is a polymorph of beryl, so it is a beryllium aluminium silicate. So it's just formed during the synthetic growth process at a different pressure temperature combination. And with the nail head inclusions, when you see them within hydrothermal grown emeralds, you'll notice that they're all pointing in the same direction. So they're all parallel to each other and they're all going the same way. So this is a feature that you can see in hydrothermal emeralds. Other features you might see in these stones are veil-like feathers and also metallic inclusions. These are often known as breadcrumbs and can be whitish or metallic in appearance, or even gold, because Byron creates them within a gold-lined autoclave, so gold flakes can get into there. So these are other features that you might see. People may ask that when you do have this set of features, for example, the veil feathers and the metallic inclusions, and even the nail heads, I guess, could be confused with comet-like structures as well. How do you know the difference between this synthetic and also then your flux-grown synthetic, because those features cross over? The main differences would be within the flux that's trapped in your flux feathers, translucent. This is translucent and whitish or orange in appearance. And then also this hydrothermal growth pattern in your hydrothermal synthetics. So this is always present in your hydrothermal grown synthetics for emerald, ruby, sapphire. So this, again, is very different to your flux. So that's how you separate those types of synthetics apart. And moving on now to our last gemstone that we're going to talk about in this lecture. So this is synthetic diamond, also known as laboratory grown or lab created diamond. So in some places we're moving more to saying lab grown diamonds, particularly in the USA. So this can currently be made with two main types of synthesis processes. One is high pressure, high temperature synthesis. So this is known as HPHT. Often when we're talking about HPHT synthetics or HPHT diamonds, it's always best to mention the fact that you're talking about synthesis, because HPHT is also a treatment in diamond as well. So as a habit, I try and say HPHT synthetic or HPHT treatment, depending on what I'm talking about. But HPHT synthesis, so this was first created in 1953 by General Electric. And no, it wasn't. 1953 by, what is it? ASEA, so ASA. So in 1955 by General Electric. Sorry about that. And these were created originally first for industrial purposes, but in the 1980s we were able to create gem quality HPHT synthetic diamonds. But at first, gemologists and the trade in general didn't worry about these stones, because when they were created, the first of these stones were these yellow, brownish yellow, really intense colors, and often were full of metallic inclusions. So they weren't that hard to identify. But nowadays, the quality of these stones has really improved. Most that are being made are colorless and relatively inclusion free. So now they have become a lot harder to identify. And this has really all been happening within the last 10 years. The other type of synthetic diamond that is on the market is CVD diamond, or chemical vapor deposition. So these are grown, wow, within a vacuum, if you like. So we have the chemicals going in, which is methane, CH4, and this is ripped apart in a plasma and deposited on these crystal seeds. And these have also been created since the 1950s, 1956, but these were not made in gem quality sizes or in gem sizes until really the last decade. So these only in the last decade have come into the gem market, and there are millions of carats being created every year through both processes. So these are very, very prevalent within our industry in all sizes. So the largest HPHT synthetic diamond that's been made and cut was just over 10 carats. So there's a blue HPHT diamond over 10 carats and a colorless diamond over 10 carats. And for CVD, these have topped for cut gems around 5 to 6 carat. They haven't got any bigger than that yet. So let's have a look at these synthetic diamond crystals, because when we have a look at the crystals, we can tell them apart really easily. So we have our natural diamonds, which grow as octahedrons. This is a very well-formed diamond crystal, often known as a glassy. And yes, it is natural. This has not been cut and polished whatsoever. Hard to believe at first, isn't it? So absolutely gorgeous. This is our natural diamond crystal showing that octahedral form. HPHT diamonds, these grow as truncated crystals. So these are either cubes with their corners cut off, so truncated cubes, or truncated octahedrons. So again, an octahedron with the corners truncated off. And these are known as cubo-octahedrons. So it's a combination form of a cube and an octahedron. And in CVD, well, you would never think that this was a diamond at all. Really, the outline depends on the shape of the crystal seed that they grew on top of. So this can be all sorts of shapes, but often they just use square or round seed crystals. And when the diamond starts to grow on these crystals, they grow in just one direction, which is upwards. So these crystals can be wafer thin, or they can get thicker and thicker until they are a thickness we can cut from them. So when they're looking like this in their crystal form, well, we can tell the difference quite easily. But once they're cut, that's where the fun really begins. And this is a real challenge for gemologists and dealers and valuers all over the world at the moment, especially where the prevalence is ever increasing for synthetic diamonds. So, how can we identify them? Well, let's talk about HPHT synthetics first of all. Sometimes there might be observations that can help us identify these stones. So first off, because these are created within a metallic flux under high temperature and high pressure, we can have some of this metallic flux trapped in the growing diamond. So sometimes you end up with these metallic inclusions inside the stone. So these will be heavily reflective and also often of angular or rod-like shapes. When it comes to another little test that we can do for this feature, these inclusions where they have a lot of iron content within them, these are magnetic to a very strong rare earth magnet. So this is something that natural diamonds cannot do. Natural diamonds are not magnetic, but these HPHT synthetics can be if they've got a high amount of magnetic inclusions inside. Another feature that we can look for in these gemstones are color zones. So natural diamonds can have color zones within them, but in synthetic HPHT diamonds, they have very particular shapes, and these really reflect the growth of this synthetic. So they're reflecting the cubo-octahedral growth that they grew within. And these shapes are either known as an hourglass color zone, which is what's shown here within this picture. If you turned your head to the side, you would see that hourglass shape. Or it could be called a Maltese cross color zone, when there's two of these hourglass color zones, but at 90 degrees to one another. That's a Maltese cross. So these are seen in some HPHT synthetic diamonds, but only those that show colour. So only in your yellow or your blue synthetic HPHTs, or maybe if they've been treated afterwards to become another colour. In regards to observations in your CVD synthetic diamonds, observations of internal features aren't going to help you because where it is grown within a vacuum, the only thing that can get trapped inside these growing crystals are graphite inclusions, which can sometimes form on the surface of the growing crystal. A graphite inclusion, well, you tell me how it looks different to any other black mineral inclusion that can form within natural diamond. It looks pretty much the same. So therefore, there are no observational features of internal features for CVD diamonds. So how can we identify synthetic diamonds? Well, there are a few things that we can do as basic gemologists, and then we might have to also then consult a lab for some help. But what we can look for, first of all, is that lack of natural inclusions and lack of natural features. So there are a whole host of different inclusions that can occur naturally within diamonds. All of these can help prove that it's of natural origin. So really it's those that are lacking these inclusions that could be synthetic, or a very high quality natural. We can look for inclusions or features that indicate synthetic origin, like those that we discussed in HPHT diamonds. And also a nice easy one that don't forget about this because this can really help you out is looking for laser inscriptions. So most diamonds have been graded by laboratories nowadays, especially any of those of a large size or any really 30 points and over if they have a good clarity. So therefore, have a look on the girdle of the stone. There might be an inscription on the side of the stone. If it's synthetic, it might say that it's synthetic, like this picture here. So that's our job done when you see this. Oof, easier than you thought. They might, instead of saying lab grown, they might have the name of the producer. So for example, they might have, there's a symbol for lightbox diamonds, which is an internal laser inscription in those diamonds. Also, it might say G Pol, or any of the manufacturers might inscribe their name onto it. Not to say this can't be polished off, but worth a look. Also, for natural diamonds, if they've been certified by a laboratory that laser engraves everything that it grades, such as Gme-A, you might be able to look for a Gme-A number, so a report number, which can be put onto the girdle of the stone as well. And this can either be searched online to get its corresponding certificate, and you can find out whether it's of natural origin, because the report will state that. So easy one to look for. Don't forget just to check for laser inscriptions. That's it for observations, unfortunately. But other things that we can do is look for UV testing. I'll talk more about that on the next page. But if we cannot conclude the origin of the stone at this point, so there's nothing visually or with UV that can help us, that's when we'll have to get a bit more into technology. So we can look at screening tests that might be able to help us determine natural or synthetic origin, or some advanced tests. So often advanced tests often require expensive pieces of equipment, so you may have to send the stone to a lab. For diamonds, it's not such a big deal to send to a lab really, because so many diamonds now are expected to have a certificate if they're being sold and traded. So often they are accompanied with a report. But on the occasion that they're not, let's have a look at what we can do. So the first test that we can do, and this can be done in any gem lab really, or even your setup at home, is to test for fluorescence. Now, first thing to know, not all diamonds fluoresce. Only about 30% of natural diamonds fluoresce, so about a third. And then only, they say a bit less than that, so 25 to 30% of synthetic diamonds fluoresce. So not all diamonds fluoresce, but if they do, depending on how they fluoresce, in what light source, that can tell us whether it is of natural or synthetic origin. Because natural diamond, if it fluoresces, will fluoresce strongest under long wave UV light, and synthetics, if they fluoresce, will fluoresce strongest under short wave UV light. So that's a great way of testing these stones, particularly for your colourless stones, but also it will work for your yellows as well. When it comes to phosphorescence, so this is the emission of light after it's been exposed to UV. If a natural diamond phosphoresces, this will only occur after long wave. If a synthetic diamond phosphoresces, this will only occur after short wave. So that's something else that can be helpful. And lastly, we can look at the colors of fluorescence as well. So natural diamond mainly fluoresces blue, can fluoresce other colors as well, such as yellow, green, white, red, but the main color is blue. When it comes to your synthetics, they will mainly fluoresce orange to yellow under shortwave. So this can be really, really helpful as well. But the main point is where they fluoresce, so which light source they fluoresce strongest under. That can be the biggest clue. If your diamond doesn't fluoresce, that's when you can move on to screening tests if you want to. Now, screening tests, these have been specifically developed to be able to be used with ease and to tell you whether your stone is of natural origin or if it's harder to tell, so it referred for further tests. So it might be natural, but it might be a synthetic as well. So that's how it separates them, either telling you it's a natural diamond or by saying, oh no, we're not sure, do some more tests. Most of these screening devices have been made for colorless to near colorless diamonds. The reason for that is that it's based usually on testing for diamond type. So really we have to pinpoint just one color to be able to do that effectively. And also this is the most commercially important color for diamonds, really, because most of them are colorless that are being created. But otherwise, these screening tests are quick and easy to use. They separate out our natural diamonds from stones that might be either natural or synthetic that need further testing. They can be used with no formal training, just a quick instruction or, a demonstration. Often they're just simple button push operated machines, and it will either say pass, it's a natural diamond, or refer, do some more tests. So foolproof, really. And like I said, it's often based on diamond types. To explain the screening test coming up, I'm going to give you the quickest lesson ever on diamond types. So, when it comes to diamonds, we separate them into diamond types based on their impurities. So that's other elements within the structure, trace elements, really small percentage. We either divide them into type 1 diamonds. These are those that contain nitrogen, and we separate those into type 1A, which are colorless to slightly yellow in color, or type 1B, which are often a much more vivid canary yellow in color. Then we can have type 2 diamonds. So these are those that do not contain nitrogen, but may contain other impurities. Type 2A are colorless and contain no impurities that have any effect on the stone. And then you have type 2B, which are blue because they contain boron within their structure. Now, why I'm telling you this is because type 1A diamonds are always natural. There is an argument that you could treat a synthetic type 1B diamond very heavily with HPHT and make it into a type 1A, but that would still be bright yellow. So for a colorless stone that we're testing with this piece of equipment, if it's a colorless, near colorless stone and it's a type 1A, it's natural, no question. All the other types can be natural, but very rarely occur in nature. So all these other types make up less than 2% of natural diamonds, but all synthetic diamonds will be of this diamond type. So for our colorless stones, whether it's natural or synthetic, if it's not a type 1A, it's going to be a type 2A. So that's how we can separate the types out. So with the different screening tests that we have, I'm just going to run through these and what they base their testing on. The DTC Diamond Shore, so this is by De Beers, this will detect one of the lines caused by nitrogen in type 1A diamonds. So it detects this line at 415.2 nanometers. It's known as the N3 color center. But if a diamond contains this line, it's natural. So the DTC diamond sure separates type 1A diamonds so it can pass all of those that have this line within it and refer all the others that do not for further testing. So easy. Other screening tools, we have the HRDD screen, the Presidium Synthetic Diamond Screener, and also the SSCF Diamond Spotter. This separates diamonds based on whether they are a type 1 or a type 2 diamond. So again, you push a button. If it's a type 1, they know it must be natural if it's colorless. And if it's a type 2, then they say, oh, you must do more tests. Because either it's a rare type 2A natural or it's a synthetic type 2A. Another piece of equipment that can be classed as a screening test, I also classed it as an advanced test because it does both, is the Magilabs EXA. And this tests phosphorescence. So if a stone phosphoresces after exposure to shortwave, if it does, there is a setting on it that can just pass the natural or refer for synthetic. So really, really handy handy tool, even if you don't know how to use the advanced equipment. More advanced tests that are out there, most of these have been created specifically for this distinction between natural and synthetic diamonds. But we have the DTC Diamond View. There's another machine or test that you can do called cathodoluminescence that does a similar thing. But this machine looks at growth patterns within the stone. And from what we looked at earlier with the crystals, depending on how the stones grew, we can have a look at these different patterns and separate out whether they're natural, HPHT synthetic, or CVD. So if we have a look at this piece of equipment here, this is the DTC Diamond View from a couple of decades ago, I believe. So this is an older version. But on the screen here, we can see this diamond, which is fluorescing blue. And then also you have some growth features, and you can see that they're octahedral in shape. That's one of the patterns that natural diamonds can show under this test. HPHT diamonds will have this truncated appearance to them. And that's because their crystal growth is cubo-octahedral. This is showing you the cubo-octahedral growth pattern. So you can conclude that this one here is an HPHT synthetic diamond. And CVD diamonds, due to their layered growth, they end up having this layered growth pattern. So it kind of looks like striations within the stone due to that layered growth during creation. So that's how you can tell it's a CVD diamond. So with this advanced test, it's a bit harder to use. So often this is why you only find it in labs by people that know exactly what they're looking for, because it's a bit more than just pushing a button for these advanced tests. Other machines that have been created for determining synthetic versus natural diamond are the De Beers Synth Detect and also the DTC Diamond Plus. These both work on photoluminescence. Also, you have the Yehuda Sherlock Holmes detector, the Magilabs EXA, which I've already mentioned, and also the IIDGR PhosView, which is by an arm of De Beers. This can look for diamonds based on their phosphorescence. So these basically you can bulk test with these or even do set jewelry, and it will highlight any that are phosphorescing, and therefore you can point out and pick out all of the synthetics that way. Also, some advanced equipment such as the FTIR, Fourier Transform Infrared, that can help you out as well, because that does a chemical analysis of the stone. So it can tell you, what the stone's made out of, and if there's any impurities within the stone, that can also help identify the type of diamond and therefore the likelihood of it being natural or synthetic. So that's all we're going to cover today. So just to cover the learning outcomes as a bit of a summary. So in regards to definitions, natural materials. So natural materials are those that have been formed by nature without any human interference or modification other than fashioning. And then artificial materials, well, those have been either partly or fully created. So these have been completely manufactured just as a part of the stone or as a whole. And these can exist in nature and be classed as synthetics, or they can be a whole creation from our imagination as well. Synthetic materials are very particular types of materials, however, that have that natural counterpart. So they have a mineral in nature that has the exact same chemical, physical, and optical properties as the one that's grown in a lab. When it comes to synthetics, key takeaways to know is that not all gemstones can be synthesized. So really it's only a select finite list currently of stones that can be. We can identify these stones by signature features. So we're looking mainly for inclusions within the stone or particular test results. And these will depend on the type of gem that we're looking at and also the method of synthesis that it's been created by. If there are no uh, if there is no evidence to say either way whether it is a natural or a synthetic, so there's no internal features we can see, no test results that can help us, that is when you will need advanced testing to help you identify the stone. You can't really conclude without concrete evidence. It's not wise. That's when expensive mistakes can happen. So some of these stones do have specific responses to some gemological tests. Oh, I've got American there. And if there are no features which can conclude synthetic or natural origin, you'll have to send it for advanced testing if you want to know, if you need to know the origin. Okay, that's where I'm going to end it. So thank you so much for all your questions. Thanks for sticking around. Contact me if you want to ask any other questions, and that would be fantastic. But otherwise, I hope you have a great rest of your day. Thank you for listening. I hope to see you next week for field gemology in the UK. So thank you. Bye-bye.